This video is going to go over chapter 3.4, real zeros of polynomials. So as we can see here in this first example, I have x minus 2, x minus 3, and x plus 4. And notice when you distribute everything, the constant that we get is 24, and 24 is actually these numbers multiplied together. So negative 2 times negative 3 and 4. So generalization of this observation is our rational zeros theorem. So if a polynomial has integer coefficients and p of q, where pq is in lowest terms, is a rational zero of f, where p and q are integers, then p is a factor of the constant coefficient of a naught, which is this one, and q is a factor of the leading coefficients of an. That might look a little confusing, but it all comes down to basically that our possible rational zeros are factors of the constant term over factors of the leading coefficient. So we have factors of a naught over factors of an, basically. So here in this example, we're going to list all possible rational zeros of negative x to the fourth plus 3x squared plus 4. So we're just going to list our factors of our constant 4. So factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4. And then we're going to list factors of our leading coefficient of negative 1. So these factors are plus and minus 1. So basically our possible rational zeros are any combinations of these. So I list my factors of 4 up here and my factors of 1, or negative 1, sorry. And then we're going to divide each by plus or minus 1, basically. So in this case, since it's just 1, we're going to get just the same factors at the top. So we just have plus or minus 1, plus or minus 2, plus or minus 4. So now these are our possible rational zeros that we can have, this list here. So we can actually test each value in f to see which ones equal 0, which means that it would be a 0 of our polynomial. So f of negative 2 is 0, and when we plug in 2 for f of 2, we get 0. These other ones don't work out. You could try them if you'd want. So we know negative 2 and 2 are zeros. So here's the steps of how to find the rational zeros of a polynomial, is what we just did. So we're going to list all the possible rational zeros using the rational zeros theorem. And then we can use synthetic division to evaluate the polynomial at each candidate for the rational zeros that we found in step 1, instead of just testing each value. And when the remainder is 0, and we're going to note the quotient we have obtained, and then we're just going to repeat that, and whenever we basically, so we find our zeros using the rational zeros theorem, which is this. And then we use synthetic division once we found our zeros. And then we're going to find basically our other zeros using a zero we have already obtained. So here's an example of doing that. So I'm going to write the polynomial p of x equals 2x cubed plus x squared minus 13x plus 6 in factored form. And then I'm going to find all the zeros. So by the rational zero theorem, we have the possible rational zeros are our factors of our coefficient, or factors of our constant term over factors of our leading coefficient. So our constant is 6, and our leading coefficient is 2. So we just find those factors. So we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And these are all going to be over plus or minus 2 and plus or minus 1. So here I put all the factors over plus or minus 1 here, and then all the factors over plus or minus 2 here. And then we get all these. So if I simplify each by dividing, and then if I get rid of duplicates, I end up with this list. So to check which one of these is actually a possible, which one's actually a 0, we can do synthetic division. So I could use test the value 1, and I test that value, and I do not get a remainder of 0, so that is not a 0. And then I test the value 2, and I get a 0. So 2 is a 0. So there, I could have also just plugged in 2 and 1, 2 here, and then solve it. But sometimes doing synthetic division is easier. And then that way, I could get the factored form here, and then solve for remaining 0. So I'm not plugging in all my values and testing them. So I just tested 2. So that means that x minus 2 is a factor since it's a 0. And then I'm left with 2x squared plus 5x minus 3 from our synthetic division. So now I know how to factor 2x squared plus 5x minus 3 to find the remaining zeros. So I go ahead and do that. And I get 2x minus 1 and x plus 3. Therefore, our zeros are 2, 1/2, and negative 3. Okay. So now, in this example, we're going to find the zeros of x to the 4th minus 5x cubed minus 5x squared plus 23x plus 10. So since our leading coefficient is 1, all of our rational zeros are basically just going to be from the factors of 10. So I have plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. So I'm going to go ahead and start with testing 1. I do synthetic division. I don't get 0, so this one is not a 0. I do 2. I don't get 0, so 2 is not a 0. I test 5, and finally I get a 0 here. So yes, it's a 0. So now I can have x minus 5 as my factor, and then I have x cubed because our polynomial is x4. So our 1 is x cubed, which is a degree lower, minus 5x minus 2. And now I could do x cubed minus 5x minus 2 and use my rational roots theorem. So, because the leading coefficient's 1, it's the same thing where just the factors are going to be from negative 2. So it's plus or minus 1 and plus or minus 2 are the possible factors. However, we already know that 1 and 2 don't work. So since they don't work for this, as a 0, it's not going to work for our x cubed. So we could just try negative 2 and negative 1. So I start with negative 2, and I got that, and it works. So negative 2 is a 0. So now I have x minus 5 times x plus 2 as my factor, and I'm left with x squared minus 2x minus 1. So that's something I know how to do. If I try to factor it, it doesn't work, but I could do my quadratic formula. So I do that, and I get 1 plus or minus square root 2. So we know that our zeros are 5, negative 2, and 1 plus or minus square root 2. Okay, so here we have a helpful rule in eliminating candidates from a lengthy list of possible rational roots. So sometimes we have really long lists of factors and we want to see, okay, which one should we test? So I'm going to start with a definition first before we find this helpful rule. So if p of x is a polynomial and we have descending powers of x, then a variation in sign occurs when adjacent coefficients have opposite signs. So here's our polynomial, and here we have a variation of sign because we go from positive to negative, so the blue is the variation. Then we go from negative to positive, so that's another variation there. And here we don't have a variation because it's from negative to negative. Here we don't because it's positive to positive, but here we have positive to negative. So this polynomial has 3 variations in sign. So this rule is just Descartes' rule of sign. So let f of x be a polynomial. So we have that the number of positive real roots of f is either a, the same as the number of sign changes of f of x, or it's less than the number of sign changes of f of x by a positive even integer. But if f of x has only one variation in sign, then there's just exactly one positive real zero. So the number of negative real roots of f is either the same as the number of sign changes of f of negative x, or it's less than the number of sign changes of f of negative x by a positive even integer. And then if f of negative x has only one variation in sign, then there's only one negative real zero. So we're going to go ahead and use this rule. So in this example, we're going to determine the possible number of positive and negative real roots of f of x equals x cubed plus 2x squared plus 5x plus 4. So here we could see in f of x, we don't have any sign changes. So we're not going to have any positive real zeros. And we plug in negative x to see how many negative real zeros we have. So we see that we have 3 variations in sign. That means that there are 3 negative real zeros or 3 minus 2, because it could be either the same as the number of sign changes or less than the number of sign changes by a positive even integer. So the greatest even integer that we have that's less than 3 is 2. So we have 3 minus 2 equals negative, or 1 negative real zero. So we can see that the possible rational roots are plus or minus 1, plus or minus 2, and plus or minus 4 using our rational roots theorem with the coefficients here and the constant and their factors. But we could use the Descartes' rule of sign. That informed us that there are no positive real roots. That means that the only possible rational roots we could have are negatives. So they include negative 1, negative 2, negative 4. And we use synthetic division to test, and we find that negative 1 is a root. So we can see that negative 1 is a root, and the other two are actually going to be complex conjugates, which we will learn about and find later. Okay, so now we're going to go over upper and lower bounds. So we say that A is a lower bound and B is an upper bound for zeros if every real zero, C, is greater than or equal to A and less than or equal to B. So A is our lower bound because it bounds C from below, and B is our upper bound because it bounds C from above. So we have our upper and lower bound theorem. So we have P as our polynomial. So if we divide P of x by x minus B with B greater than 0 using synthetic division, and if the row that contains the quotient and remainder has no negative entry, then we can say that B is an upper bound for real zeros of P. If we divide P of x by x minus A with A less than or equal to 0 using synthetic division, and if the row that contains the quotient and remainder has alternate non-positive and non-negative, basically saying it has positive and then switches to negative, then A is a lower bound for the zeros of P. So here we have an example. So we're going to show real zeros of the polynomial P of x equals x to the fourth minus 3x squared plus 2x minus 5 are between negative 3 and 2. So we would be essentially testing that negative 3 is our lower bound and then 2 is our upper bound. Okay, so we'll divide P of x using synthetic division by x minus 2 and x plus 3 essentially, because our C is negative 3 and our C is 2. So we do synthetic division, and we can see that when we divide by 2, they're all non-negative, which satisfies our condition for an upper bound. If we divide by negative 3, we get alternating signs. We have positive, negative, positive, negative, positive. So that means negative 3 is lower bound. So by our theorem, negative 3 is a lower bound and 2 is an upper bound for zeros. And since negative 3 and 2 are not zeros, because our remainders are not 0, they're not zeros. So that is just like saying that all zeros lie between those numbers, and negative 3 and 2 aren't zeros in themselves. So our bounds aren't zeros. So yeah, all zeros lie between these numbers. So I'm going to go ahead and continue the next video with chapter 3.5. Follow me there.